All right, everybody, welcome back. This is the second video for Unit 2, Section 1 of AP Calculus, defining average and instantaneous rate of change at a point. So picking up where we left off, in the last video we talked about how the average rate of change is equal to the slope of a secant line over an interval, and that the instantaneous rate of change was the slope of a tangent line at that point. And we defined each of these. This was the difference quotient, was our average rate of change. And then the instantaneous rate of change was our limit of a difference quotient. And of course, the difference quotient is just, really a slope formula between 2 points. We looked at a couple of different ways to, think about that and set that up. But in reality, all we're really thinking of when we're thinking of average rate of change is a slope through 2 points. And when we're thinking about the instantaneous rate of change, we're thinking of a slope at 1 point. Okay. In this video, what we're going to do is we're going to look at a couple of examples. The first one is adapted straight from free response question number 1 from the 2021 AP Calc AB exam. And so a fairly recent free response question that we've adapted and borrowed the data from and twisted around the question a little bit. And then we're going to look at another problem where we're finding the rate of change from an equation. So we're going to start with one example from a table and then look at another example from an equation. So here we go, example 3. The density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by the function f, where f of r is measured in milligrams per square centimeter. So all the important units are there, and we see they're given in the table as well. Values of f of r for selected values of r are given in the table below. Part A. Use the data in the table to find the average rate of change of the density of the bacteria population on the interval from 1 to 4. Include units of measure. So we're talking about this interval from 1 to 4. So that's telling us that we're using these 2 points. And since we're finding an average rate of change, all we're going to do is find the slope between those 2 points. And so we're going to go ahead and set that up. 18 minus 2 over 4 minus 1. And that's going to be 16 over 3. Now, as far as units go, f of r, which is our numerator, is measured in milligrams per square centimeter. And r is measured in centimeters. So this is milligrams per square centimeter, represents our numerator. Centimeters our denominator. So it's going to be milligrams per square centimeter per centimeter. And I prefer to write it that way because it's descriptive based off of the units in the problem. Some people might let you abbreviate that milligrams per cubic centimeter, but I really think that it's more appropriate in this context to say it as milligrams per square centimeter per centimeter, since it depicts the density per distance, in the unit instead of being some other more nebulous unit. All right, part B. Use the data in the table to approximate the instantaneous rate of change at time t. So on our AP exam, when we're trying to approximate an instantaneous rate of change, our only real option for approximating the instantaneous rate of change is by using the average rate of change from the table. Okay, when we're trying to find instantaneous rate of change from a table, it's impossible to actually find it. We're going to approximate it, and the way we approximate it is by using the data in the table. I always recommend to people that when you're finding or approximating the instantaneous rate of change at a particular time, that you find the time interval that that point is in and find the slope of that time interval. Actually it's not at time t equals 2, it's at radius r equals 2. We'll have to fix that. And so we're finding it at radius r equals 2, but that's contained in a bunch of different intervals. It would be a little bit different if we were finding it at radius 3. 3 falls in between 2.5 and 4, so I would use those 2 points to approximate the instantaneous rate of change. But the radius of 2, there's actually, since it's one of the given points in the table, I actually have 3 options as far as approximating the instantaneous rate of change. I can use the interval from 1 to 2, since 2 is in that interval. I can use the interval from 2 to 2.5, since 2 is in that interval. And I can also use the interval from 1 to 2.5. So there's 3 different ways, since we're actually approximating the instantaneous rate of change at one of the given values in the table. There's 3 different ways we can approximate this and still have a workable answer for us. So let's go ahead and use the first one, the interval from 1 to 2. So we've got 6 minus 2 over 2 minus 1. So that's going to be 4. Or we could do 10 minus 6 over 2.5 minus 2. It's 4 over 0.5, or 8. Or we could do the widest interval, 10 minus 2 over 2.5 minus 1. That's 8 over 1.5, or 16 over 3. Any of these 3 numerical answers would be okay for this problem, and we want to make sure that we have our units, which are going to be milligrams per square centimeter per centimeter per square centimeter per centimeter. Okay, so whichever of those 3 methods you would choose to approximate this, the units go with every one of those answers. All right, on to example 4. The number of gallons of water in a storage tank T minutes after the tank has started to drain is Q of T equals 80,000 minus 8,000 T plus T squared. Write an expression to represent how fast the water is running out of this tank at time T equals 5 minutes, and then use the expression to find this rate of change. So I'm going to actually use the second style of difference quotient here in order to do this problem. I'm going to find the limit as T approaches 5 of Q of T minus Q of 5 all over T minus 5. And now we can go ahead and find the instantaneous rate of change. Since we're looking for how fast the water is running out at time T equals 5, that's our indicator that this is instantaneous rate of change at time T equals 5 and not over the interval from T equals whatever to T equals 5, which would be indicative of an average rate of change. All right, so we go ahead and put the pertinent information in here. Q of T is 80,000 minus 8,000 T plus T squared. Q of 5 is what I get when I substitute 5 into this expression, which is 80,000 minus 40,000 plus 25. I've got all of that over T minus 5. That's the limit as T approaches 5 of that whole expression. And so now the limit as T approaches 5, I'm going to manipulate this. The 80,000 and minus 80,000 balance each other out. And so what I'm left with, and I'm going to change the order here, T squared minus 8,000 T, and it's going to be plus 39,975 all over T minus 5. Now I'm going to try and take this limit algebraically, and when I try and take this limit algebraically, I try to substitute 5 into the numerator and 5 into the denominator. If I substitute 5 into the numerator, I get 0. If I substitute 5 into the denominator, I get 0. So this is one of those 0 over 0 indeterminate forms. So I'm going to want to go ahead and factor and cancel in order to find this limit algebraically. Now I know that since 5 makes the numerator equal to 0, that means that T minus 5 is one of the factors of that numerator. And that's really helpful for us to know that. It makes it a whole lot easier for us to find the factorization of this. Now, what do I need to multiply by T to get T squared? I need to multiply that by T. And what do I multiply by 39, or by 5? minus 5 to get 39,975. That's minus 79.95. And now we'll cancel out the common factors from the numerator and the denominator. And this becomes equal to the limit as t approaches 5 of the quantity t minus 7,995. We substitute in, and we end up with negative 7,990. And my units, my numerator here was the number of gallons of water, and my denominator was my unit of time. So our unit for our final answer here is going to be gallons per minute. Now realize, I could also have set this up as using the other difference quotient. I could have set it up as the limit as h goes to 0 of q of 5 plus h minus q of 5 all over h, and done the algebra related to that. It would have been looked a little different, but in the end we would have ended up with the same result. All right, okay, that's the end of this video and the end of the lesson for section 1 of unit 2. See you all next time. Have a great rest of your day.